Hello, everyone. We are ProtectE Consulting, a company that was created with the idea of protecting the environment and provide support and solution to business. Today, we'll be presenting our work on the dynamic modeling and optimization of the Northwest Water Reclamation Facility in the Tampa area. ProtectE is composed by a team of excellent engineers in order to ensure and warranty the most efficient and effective solution to our clients. The designated team for this project is the process engineer Victor Johnson, reliability and optimization engineer Donald Corca, the design engineer Brandon Serra, our environmental engineer Daniela Pecci, and myself, Emilia Serrano, as an operability engineer. The scope of this project is to develop a dynamic simulation of the Northwest Water Reclamation Facility and to provide a summary of effluent and effluent waste composition and unit operations, as well as analyze the process and optimize it regarding to the energy consumption. The Northwest Water Reclamation Facility utilizes a full biological process and is currently serving around 64,000 people in the Hillsborough County. The current plant capacity is 10 million gallons per day, and after the expansion, the capacity will go up to 30 million gallons per day. This expansion is being made with the idea to cover for other incorporated areas as the Del Mabry and River Oaks facility.
As previously mentioned, the biological process is known as Bard-and-Foe. The 5 stages are a modified version of the original process, with the modification being an anaerobic basin added to the beginning for fermentation. Every train, as shown in this slide, consists of one fermenter followed by an anoxic phase, then an aerobic phase. A portion of the influent will be recycled into the first anoxic phase, and the rest will go through a second anoxic phase and aerobic. Finally, the influent will go through a clarifier where the solids will separate from the water. The goal of this process is to remove phosphorus, nitrogen, CBOD, also known as carbonaceous biological oxygen demand, and sludge. The final touch is to then run the effluent through a filter and chlorination dechlorination chamber. The preliminary step is the headworks, where the raw influent will pass through a bar screen. Large objects and non-dissolved plastics will be cleared and then disposed of as grit. The first phase of the Bard-and-Foe process is fermentation, also known as the anaerobic tank. There are no nitrates or dissolved oxygens present, making the conditions totally depleted of anaerobic sources. This environment will force the production of phosphorus accumulating organisms, PAOs, who will create volatile fatty acids and orthophosphates. This will prepare the influent for denitrification in the next phase. Denitrification occurs in the anoxic basin. Recycled influent will mix with the stream entering this phase, adding nitrates, producing an anoxic environment. The BOD, also called bugs, will consume the nitrates and produce nitrogen gas and carbon dioxide. However, most of the nitrogen exists in the form of ammonia. Thus, the process must continue to the aeration basin. Here, oxygen is bubbled in and mixed to finally create an oxygen-rich environment for the bugs. Ammonium will be converted into nitrates, followed by denitrification again. What will be left is sludge and water with a small amount of microorganisms still present. This stream will move into a clarifier, a very large tank that will hold the influent as still as possible, while skimming the top and bottom of the tank. The sludge skimmed has two parts: volatile suspended solids and sludge, which is collectively called total suspended solids, TSS. A portion of this TSS is recycled back to the beginning, and the rest is sent to a biological treatment plant as waste. The final effluent is put through a chlorination chamber, where bleach, sodium hypochlorite, at 12% concentration will sanitize the stream, and sodium bisulfite will be used to return the pH to 7. A sand filter is also used to remove 99% of impurities left. This water is then used as a utility and pumped back into the aquifer.
The key assumptions we took in consideration were that the plant never stopped working. It runs 24 hours a day, the 360 days a year. The influent and effluent concentration stays constant during a certain hours of the day. Brass gases please stay constant. The process is not affected by the rain or any other environmental phenomenon. The volatile suspended solid is 0.63 of the total solid suspended, and the concentration of the COD is 2 times concentration of BOD.
2016 influent flow rate data during different hours of the day was analyzed, and it is found that the average flow rate changes a lot from 3 to 9.2 million gallons per day. Graph shows that off-peak hours are usually from 12 a.m. to 7 a.m., and after that it starts picking up to slow down again after 11 p.m. This doesn't mean that most of people shower late at night because time needed for wastewater to reach the treatment plant is not taken under consideration. It was also found that during holidays like Thanksgiving, 4th of July, Halloween, etc., influent flow rate would reach its maximum values. This pattern of influent flow rate will come in importance later on during optimization. Wastewater that comes into treatment plant is composed of different elements. The main parameters that describe effluent characteristics are CBOD, or carbonaceous biochemical oxygen demand, TSSS, total suspended solids, TN, total nitrogen, and TP, total phosphorus. Their concentration vary a lot during a day, reaching its maximum values as shown in the third column of the table. Influent concentrations for biowind simulation are taken to be CBOD 242 milligrams per liter, TSSS 278 milligrams per liter, TN 48 milligrams per liter, and TP 8 milligrams per liter. As I mentioned, concentrations are in milligrams per liter, but the total mass of these elements in pounds per day is very significant. For this reason, it is important to protect the environment by performing an efficient water treatment.
The simulation was performed under the normal operating condition with an average temperature of 25 Celsius. The rust and the wash ratio was 60% and the internal recycle was 70%. The aeration power was 300 horsepower or 224 kilowatts. The reaeration power was 25 horsepower or 19 kilowatts for each train. The aluminum flow rate was 457 gallons per day with a pH of 2. The clarifiers were 20% underflow fraction and the dewatering unit was 10% underflow. The, the splitter fraction was 50% for each one. The simulation was run for 60 days to achieve the steady state condition. The following graph shows the variation characteristic for the most important compounds and elements in the wastewater treatment process. The only concern present in the effluent composition was the total nitrogen concentration, with an average of 6.5 milligrams per liter of water, which was above the limit allowed by the EPA standard effluent concentration, which was 3 milligrams per liter of water. Based on the graph, the actual model removed most of the important compounds present in the effluent, such as total BOD, total suspended solid, or TSS, and the total phosphorus, or TP. Also, the TSS concentration present in the biological process was reduced by almost 92%, which implies that more organic material, or BOD, is needed to reduce the concentration of TN, or total nitrogen, in the effluent. As a solution, a controller was used to increase the amount of the TSS or the organic material to around 1,900 and 2,000 milligrams TSS per liter of water for each train. In order to increase the TSS, the rust in the water splitter of 2,444 meters cubed per day or 60% of the underflow clarifier was recycled to the system again for a TSS concentration greater than 2,000 milligrams per liter of water. The rust was splitter on the floor was reduced to 611 meters cubed per day, or 90% of the underfloor clarifier was recycled to the biological process again for a TSS concentration less than 1,900 milligrams per liter. In addition, the power uptake by the aeration was reduced to provide an anaerobic condition to enhance the denitrification process and reduce the operating cost. The manipulation of the power in the aerator was introduced into the system by making a small step change in the power to balance the consumption of the nitrate and formation of ammonia and nitrate in the system. A sensitive analysis of the relationship between the effluent composition and the change in aeration power was performed for the remove of the TN using the controller in BioWin. The aeration power was reduced from 224 kilowatts or 300 horsepower to around 170 kilowatts. The total nitrogen was reduced to 5.1 and 4.6 milligrams per liter. Then a range in the power aeration was introduced between 150 kilowatts for influent flow greater than 4 million gallons per day and 60 kilowatts for influent flow less than 4 million gallons per day, which reduced the total nitrogen range between 5 and 4.5 milligrams per liter. Now, the power range was reduced to 120 kilowatts and 60 kilowatts, resulting in a total nitrogen range of around 4.7 and 4.4 milligrams per liter. Net, it was decided to completely shut down the aeration power when the influent was less than 4 million gallons per day by keeping a power of 120 kilowatts when the influent was greater than 4 million gallons per day. The total nitrogen was reduced to around 4.4 and 4 milligrams per liter. Then the power was reduced again to 100 kilowatts and 0 kilowatts. As a result, the total nitrogen in the effluent was able to reduce to 4 milligrams and 3-4 milligrams per liter. As a result, the final profile for the effluent composition can be seen in the following graph. The biological oxygen demand, or BOD concentration, was with a range between 1.12 and 0.88 milligrams per liter of water. The total suspended solid, or TSS, is zero because of the dewatering unit before the effluent was selected to remove 100% of the TSS in the inlet flow. The total nitrogen concentration was established with a range between 4 and 3.4 milligrams per liter. The total phosphate with a range between 0.016 and 0.011 milligrams per liter of water. The potential of hydrogen, or pH, stayed in the range that allowed the bacteria to grow with a range of 6 and 8 pH. The ration shows the power was 134 horsepower or 100 kilowatts when the effluent was greater than 4 million gallons per day, and 0 kilowatts when the influent was less than 4 million gallons per day.
At what point can we say that wastewater is treated well enough to be discharged? In order to avoid arbitrary and relative judgment, organizations like United States Environmental Protection Agency, EPA, have developed a set of standards and regulations. Wastewater can either be discharged in the environment or it can be reused to water golf courses, backyards, etc. EPA has set regulations for both types of discharge. But for this project, we are focusing only in wastewater discharge in environment. As it can be seen from the table, EPA standards for BOD, TN, TP, and pH are met for full range of their concentration. As it was mentioned earlier, TSSS concentration cannot be estimated from bio simulation, but it's safe to assume that it falls below 5 milligrams per liter. On the other hand, total nitrogen concentration is just a little bit above the allowed limit. Reducing the total nitrogen concentration was the hardest part of this project, and we were able to reduce it to the actual concentration by playing with aerator power and RAS to WAS ratio. The fact that total nitrogen is just above the allowed limit can be perceived not as a bad thing because plant was simulated for only 1 week. Running BioWind for a full year would reduce concentration even more and satisfy EPA standards. Northwest Water Treatment Plant has a capacity of 10 million gallons per day, and for this reason, it demands a lot of energy. Energy demanded and energy supplied prior to optimization are taken from Northwest report file. After energy is converted from horsepower to kilowatts, the following data is recorded. Total energy demand is about 3,450 kilowatts. Total energy supplied is about 9,850 kilowatts, and leading to an overall efficiency of 35%. As it can be seen from the distribution pie chart, most of the energy demand comes from pumps. But we have to consider the fact that there are about 27 pumps actually working around the plant all the time. And the most energy demanded per unit comes from aerators, and we have 8 of them in the plant. In order to perform an economic analysis, a number of economic assumptions are used as follows. Plant operates 360 days a year, 24 hours a day. It's 360 instead of 365 because we are accounting for some downtime that we might expect. Also, peak hours are from November to March from 6 a.m. to 10 a.m. and from 6 p.m. to 10 p.m. and from April to October from 12 p.m. to 9 p.m. The rest is going to be considered off-peak hour. Energy charges include all costs except fuel. Also, the on-peak charge is about 3.3 cents per kilowatt hour, and off-peak charge is about twice as cheap in a 1.4 cents per kilowatt hour. Total cost is based on average energy consumption of each unit. Capital cost of the plant is about $70 million, but we will focus only in operation costs since no investment will be made. After analyzing the available data before and after optimization, we came up in conclusion that scheduling the aerators based on the effluent rate will reduce the energy consumption by 11%. Translated in money, operation cost would decrease by $72,000. This is a significant reduction of operation cost since no investment is needed to achieve it. $72,000 is achieved only by making this process more efficient.
An important aspect of this project is to take into consideration the possible health and safety risks. As a consulting group, we determined that flooding presents a big risk to the equipment as well as to the operators, and this could happen due to the overflow of the tanks that have a maximum volume of 160,000 cubic feet. In the case of a major event, electrical shock is another risk that could lead to fatalities if water came into contact with electrical equipment and personnel happened to be at the site of the flooding. Fecal bacteria can be very harmful to the human health, and this is a health risk that wastewater presents if it's not properly treated or flooding occur where the raw sewage is. A haze-up analysis was conducted with the objective of identifying the following potential problems with the system. Hazards that could potentially harm the environment or put at risk the personnel of the site, or operability problems that will cause operational disturbances or production deviations leading to undesired results. The main objective of this analysis is to assist in the determination of appropriate remedial measures. For this project, ProtectE Consulting limited the hazard study to only process critical components that could cause a major event, such as flooding, if operational failure was to occur. The critical unit operations for the treatment plant were the fermenter, where the temperature effects on the vessel were studied and the deviations and consequences were established. If the temperature rises due to an external fire, it will directly affect the activity of the bacteria. In order to avoid this, a temperature high alarm needs to be installed for the system. On the other hand, if the temperature was to drastically drop because of extreme cold weather temperature changes, this as well will affect the activity of the bacteria by decreasing the speed at which they consume organic components and could also potentially kill them. The same alarm that was installed in the case of high temperatures can be used to indicate the temperature drop. The aerator could be affected by the amount of power supplied to it. This will either increase the speed of the propellers due to a mechanical malfunction and therefore regular inspections and maintenance checkups are required. Or no power could be supplied to the aerator, directly affecting the desired concentration levels due to the lack of dissolved oxygen. And to avoid this, a backup power supply system will be necessary, such as, such as a power generator. The clarifier could have a deviation of high flow caused by a valve malfunction or a storm or heavy rain, which will cause flooding or more flow to the pump, finally damaging the pump. Actions needed for these items are to use an alarm system for the tank levels or valve failures, as well as the use of a drain valve to balance the tank level. If the flow level was to decrease due to an inlet line rupture or a flow meter transmitter malfunction, this will have a consequence of less amount of mixed liquor to the clarifier. This consequence can be mitigated by implementing a bypass system to compensate for the amount of mixed liquor to the clarifier and avoid the accumulation of wastewater in the primary treatment area, as well as periodic valve inspections to ensure their proper functioning. The environmental impact is also very important, and this is why maintaining compliance with the regulatory agencies is key to the operation of the plant. Permits such as NPDES for wastewater are very important, and this is why frequent water quality monitoring is necessary in order to stay in compliance with the permits for the site, as well as EPA effluent concentration level standards. There are two potential types of environmental impact: upland, such as sewage contacting wetlands, or marine impacts, where untreated water could come in contact with any surface water of the United States, such as lakes, bays, or rivers. Some of the conclusions and recommendations ProtectE came up with are the fact that optimizing the aerators by scheduling the amount of power input as a function of the amount of influent coming into the plant will decrease the energy cost of the site by $72,000. This should be done by implementing an automated control system that will automatically and directly manipulate the amount of power going into the aerators. Total effluent concentrations of 0.88 to 1.13 for carbonaceous biochemical oxygen demand, 0 for total suspended solid, 3.35 to 4.05 for total nitrogen. And this is still being studied in order to determine the reason of why we aren't meeting the EPA standards for effluent concentrations. 0.012 to 0.015 for total phosphorus, as well as pH level, are successfully meeting the state's requirements. Some of the recommendations that we have is that since safety of the site personnel should always come first, an implementation of the current emergency response training for the operators should be done, as well as capital upgrades should also include and consider the reliability of the system in the case of major events due to operational failures and to ensure everyone's safety as to protect the equipment used.
We would like to thank Dr. Sunol and Komar Torre, the engineering and plant supervisor from the Northwest Water Reclamation Facility, for the opportunity to visit the plant, as well as the chemical engineering department. Thank you for listening, and I hope you enjoy our presentation.